exponential decay occurs when the base of our function is between 0 and 1. And that's what we call a decay factor. So when we have y equals a times b to the x, and b is between 0 and 1, then we have what is called a decay factor. Now that decay factor is the amount that remains. So it's the amount that is retained, not the amount lost. That's important for you to understand. So when a number is decreased by 5%, the amount that's remaining is 95%. So when you find the decay factor, you have to think 100%, not plus your growth, but 100% minus your decay. Okay? So remember that 100% plus growth equals your growth factor, and 100% minus your decay is equal to your decay factor. So your decay would be the amount you're decreasing by. So 100% minus 5% is where they're getting their 95% in this little example here. Milk consumption. Since 1980, the number of gallons of whole milk each person in the United States drinks each year has decreased 4.1% each year. In 1980, each person drank an average of 16.5 gallons of whole milk per year. Write an equation to model the gallons of whole milk drunk per person. And then we're going to use that equation to find the approximate consumption per person of whole milk in 2000. Now, they're talking about whole milk because not many people drink whole milk anymore. A lot of people started drinking 2% milk. So that's why the number of gallons of whole milk has exponentially decayed over the years, because it's been replaced by something that's a little bit healthier in 2%. So first of all, we're talking about since 1990. That's important for us to know. Next thing is that it's decreased by 4.1% each year. So our decay factor, so our B value, is going to equal 100% minus 4.1%. And if I take 100% minus 4.1%, I'm going to have 95.9%. And as a decimal, that's 0.959. So my B value translates to be 0.959. So that 4.1% got me to my base of 0.959. Now, beginning in 1980, I better put that in yellow, beginning in 1980, an average of 16.5 gallons of whole milk per year per person is what was consumed. So our output is going to equal 16.5, and then in parentheses 0.959 raised to the x power. What does x stand for? X is the number of years after 1980, and y is equal to the average number of gallons of whole milk drunk per person per year. So there's our A. Now we're going to use that equation to find the approximate consumption per person in 2000. So in the year 2000, that would be 20 years after 1980. So we're going to put a 20 in for X. I'm going to put this into my calculator. I encourage you to do the same. Press pause if you want to grab your calculator and put this into your calculator and check to make sure you get 7.14 gallons drunk per person per year. And that's an example of exponential decay. So the big takeaway there is this part right here. This is a very, very, very important concept. If you don't get this concept right here, rewind, rewatch. Make sure that you really absorb that and take that in, because that right there is the key. It's the key to the entire problem. Okay, in 1990, the population in Washington, D.C. was about 604,000 people. Since then, the population has decreased about 1.8% per year. It's very interesting because I think it would be interesting to see what the population is now. Pretty sure that that downward trend continued. I just don't know if it continued at that particular decay rate. What's the initial number of people? What's the decay factor? Write an equation and then predict the population in 2010. Go ahead and press pause and see if you can come up with the answers to these 4 questions. When you're ready to check your answers, go ahead and press play. Okay, the initial amount is 604,000 because that's our initial population in 1990. The decay factor is going to be 100% minus 1.8%, which is 98.2%, which is equal to 0.982. Our equation is y equals 604,000, and then our base is 0.982. That's the amount we're going to retain, and then that's to the x power. X equals the number of years after 1990, and y equals the population in Washington, D.C. And then D says calculate it for 2010. Well, 2010 is 20 years after 1990. So we're going to put a 20 in for X. And in our calculator, you should have gotten 420,016 people for an estimated population. Hot diggity dog. Okay, tell whether each graph is a linear function, an exponential function, or neither. So we should know what a linear function is. We should know what an exponential function is. You should know the name of all of these functions. So go ahead and press pause and see if you can come up with the name for each one of these problems, and then come back and press play. Okay, this first one is linear. The second one is absolute value. We know this one, right? This one down below, do you remember what this one was called? This is what we're going to work on. This is another big unit that we're going to close up the semester with our quadratic unit. So we end Algebra 1 with quadratics, and that's what number 39 is. And then we have the exponential function right here. Exponential. Right there, number 38. Okay, important for us to know the names of those because we want to know, do we have a linear function or an exponential function? Linear is arithmetic. That's when you have a common difference. That's when you have a slope, a constant slope. And exponential is your geometric. That's when you multiply to get from one term to the next. So let's look at this first one. To get from 20 to 40, we're going to add 20. 40 to 60, add 20. 60 to 80, add 20. Our x's going up by 1, up by 1, up by 1. This right here is linear. We remember that. That's good review. This next problem, however, going from 3 to 9, we can add 6, but we don't add 6, add 6. And we know that our x value is going up constant, so our y value should go up constant too if it's linear. This one is multiply by 3, multiply by 3, multiply by 3. That is geometric, which is an exponential function. And then this one looks like we're adding 6, adding 6, adding 6, and our x's are still just going up by a constant value of 1. This is a linear function. So that's how you can tell the difference. You're going to multiply to get from one term to the next if it's exponential, and you will add to get from one term to the next if it is linear.